Hey everybody, and welcome to our second numerical analysis lecture. Today we're going to be talking about Newton's algorithm. Oh, wait a minute. We called it Newton's method before, didn't we? Yeah, we called it Newton's method. But Newton's algorithm is fine. But if we talked about Newton's method before, why are we talking about it again? We're going to view it from a different perspective. In the first lecture, we derived this using Taylor series. We can also do this geometrically. So we're looking at it from a geometric perspective. The application is the same. We want to find the solution to the equation f of x equals 0, where f of x is differentiable in the sense that all of its derivatives exist. F of x, first derivative, second derivative, third derivative, so forth and so on. At least that was the stipulation when we were looking at it from the Taylor series perspective. You know what? Looking at it from the geometric perspective, we don't really need that much. We're just going to insist that f of x and the first derivative exist. We'll get the same exact method, but the only thing that we really need to require is that f of x and its first derivative exist. Input for this algorithm, we'll have to define f of x when we write the program. We'll have to define the derivative f prime of x when we write the program. And the program will have to prompt the user for a good guess as to the value of x. And remember what x is. X is the value that makes this function f of x equal to 0. So the solution of this equation, f of x equals 0, is x. And so our good guess as to the value of x is going to be our initial approximation of the solution. And we're going to call this x of naught. X of naught is our first approximation to the solution. And as in the case with Newton's method, where we did this from the Taylor series perspective, our first approximation should be a good guess, hopefully within less than 1 unit. Also, something we have to input into the program, max. This is an integer variable. Max will be the maximum number of iterations allowed. And the reason that we have max is because this algorithm may not converge. It may keep repeating and repeating and repeating and go off into the sunset, spitting out successive approximations that don't converge to the solution x. And if that happens, we don't want this program to run in an endless loop. So we have the maximum number of iterations that will allow before either we get a solution or we decide that, you know what, given this initial approximation of x, this algorithm's not going to converge, so we'll stop. And with Newton's method, certainly a value of max equal 30 is high enough. Maybe even max equal 10. But anyway, max will be the maximum number of iterations that we allow before we decide, you know what, with this initial approximation that we gave, the algorithm's not going to converge to the solution. So we quit and we print out a message that says, the algorithm failed. Now, the last thing that we want is a value of the variable TOL, or tolerance. And essentially, this is the criterion that we use to decide that we've gotten close enough to the solution. So when we get two successive approximations whose difference is less than tau, we quit and we use the last approximation as our approximation of x. So let's say that x of 10 and x of 11 differ by less than 10 to the negative 8. We figure we're pretty darn close, and we're going to take our last approximation, x sub 11, of our approximation, our final approximation for the value of x, our solution. So this is what we use the algorithm for. This is our input. And now let's take a look at how we get Newton's method from a geometric perspective. Let's look at a graph of the function f of x. Here's what the graph of y equals f of x might look like. And remember what it is that we're looking for. We're looking for the solution to the equation f of x equals 0. Well, on this graph, this is where f of x equals 0. F of x equals 0, exactly where the graph y equals f of x crosses the x-axis. So right at this point, this is our solution x. Now, let's suppose that we have a fairly good approximation, a fairly good initial guess as to the value of x, and we call that initial approximation, or our first guess, x sub 0 or x sub naught. And let's say that maybe this is where our first approximation is. This is our x sub 0. And for some strange reason, I don't know why I'm going to do this, but I'm going to plot the point x sub 0, f of x sub 0. So that'll be right about here, x sub 0, f of x sub 0. And I'm going to draw the tangent line you son of a gun. Okay, here's the tangent. I'm not sure why I drew the tangent, but I did. And I'll write out exactly why this is important. Okay, here's the entire premise upon which Newton's method is based, geometrically speaking. Geometrically, Newton's method is based on the assumption that if x naught is a good guess as to the value of x, our solution, then the line tangent to the graph of f of x at the point x naught, f of x naught, this tangent right here at the point x of naught, f of x of naught, will cross the x-axis at a point x of 1. So here's x of 1, the point at which the tangent crosses the x-axis. Our premise is that if x of naught is a good guess as to the value of x, then the line tangent to the graph of f of x at the point x naught, f of x naught, this tangent will cross the x-axis at a point x of 1 that is closer to x than the original approximation x naught is to x. That's kind of wordy. I'll put that in parentheses. But the premise is that if x of naught is a good approximation to x, and if we draw the tangent line to the graph of f of x at the point x naught, f of x naught, this tangent line will cross the x-axis at a point that is closer to x than is x of naught. And see, that's exactly what happens here. Here's x of 1, the place where the tangent line crosses the x-axis. And notice that x of 1 is closer to our solution x than x of naught is. So that's the entire premise that Newton's method is based on geometrically. If we get a good first approximation x naught, and we draw the line tangent to the graph at the point x naught, f of x naught, that tangent is going to cross the x-axis at a point that is closer to our solution than x of naught is. That's our entire premise. And so, x1 becomes our next approximation. Since x of 1 is closer to x than is x of naught, x of 1 becomes our next approximation to x. Okay. Well, that's fine, except we don't know what x of 1 is, do we? We don't know what x of 1 is. Can we figure it out? Let's see. How do we find x of 1? Well, note this. The point at which the tangent crosses the x-axis, here's the tangent. The point at which the tangent crosses the x-axis, the x-coordinate is x1. What on earth is the y-coordinate? What is the y-coordinate where this tangent line crosses the x-axis? Well, the y-coordinate of every point on the x-axis is 0, right? So the coordinates of this point are x of 1, 0. And you know what? This is a line, and we know 2 points on the line. We know x of naught, f of x of naught, And we know x of 1, 0. If we know 2 points on a line, what else do we know? The slope. In other words, the difference of the y-coordinates over the difference of the x-coordinates. We'll let this point be our second point, x2, y2. We'll let this point be our first point, x1, y1. So let's see, the difference of the y-coordinates, 0 and f of x of 0. Difference of the y-coordinates, and then the difference of the x-coordinates, x of 1 minus x of 0. So that's the slope of our line. But this is a tangent line, a tangent to the graph of f of x at the point x naught, f of x naught. So let's write it as it really is. The slope of the tangent is equal to 0 minus f of x naught over x1 minus x of naught. Everything's coming into view now. This is the slope of a tangent line at the point x naught, f of x naught. From Calculus 1, think about this. What is the slope of the line tangent to the graph f of x at x naught, f of x naught? Isn't the slope of the tangent just the derivative? So the slope of the tangent is f prime of x naught. And I can just throw this 0 away. 0 minus f of x naught is just minus f of x naught. And you know what? We have f prime, the derivative, defined as input. So if we plug x naught into f prime, we can figure that out. We can plug x naught into the function f, which is also defined as input. So we can compute f prime at x naught because we have f prime defined. We can compute f at x naught because we have f defined. And of course, we know what x0 is. That's our initial guess. Our program prompts the user to enter a guess as to the value of x naught, or as to the value of x rather. And that first guess is x naught. We know everything in this equation except for x1. So let's solve. Recall that this is where we left off, and we're looking for the value of x1, which is our second approximation for the solution. X naught is our first or initial approximation. X1 is going to be its successor, the next approximation. So since we're solving for x1, we'll multiply both sides of the equation by the denominator here and get this. And since we're solving for x1, we'll move this f prime of x to the other side. Well, let's see. That's not exactly where we were. I wrote this down incorrectly. I wrote this down incorrectly. What this was f prime of x naught equals negative f of x naught. Okay, that's better. I'm still looking for x of 1. And so to solve for x of 1, I'm going to move this f prime of x naught to the other side. Oh, this is looking good. Now all I have to do is move x naught to the other side. Now this not only tells us how we get our first approximation after the initial approximation, but this also tells us how we get each successive approximation. So let's say we do this in terms of x of n instead of x0. Then this will be f of x of 1. This will be x of n plus 1. If the number of iterations exceeds max, then this algorithm isn't going to converge because our first approximation was not good enough. Our initial guess wasn't good enough. Now what we want to happen is this: two successive approximations differ by less than tolerance. And if this happens, We print the solution is, we print the value of x sub n plus 1, and then again we stop. And that's the derivation of Newton's method geometrically. Not bad, huh? In our next lecture, we'll talk about something called the bisection algorithm. And you'll like this. We don't really have to have a good guess for the bisection algorithm. As a matter of fact, f of x doesn't even have to be differentiable. That's interesting. So next lecture, we'll do the bisection algorithm. It has exactly the same application, but we don't necessarily have to have a good guess as to the value of the solution. We can be miles away and still have that scheme converge to the solution.